Good morning, good morning, good morning, good morning. How is everybody doing today? All right, so today we're going to be starting off on definition 17. However, quick correction to make from last time. A couple of quick corrections. First, several of you pointed out to me that I had forgotten to include the E here in my little if-then statements for definitions 15 and 16, so I did go ahead and correct those. Also, last time I said that we would be finishing up with the definitions today. I was looking ahead at what we have left to do, and I've decided actually to break up the rest of the definitions into 2 more days. So we're going to get through definitions. What we're going to try to do today is we're going to do definitions 17, 18, 19, and 20. And then we're going to leave definitions 21, 22, and 23 for tomorrow. I think that'll make for slightly shorter lessons, but for reasons that'll become pretty clear when we get to definition 20. Basically, Euclid ends up starting to cram lots of definitions into each official definition. So he starts defining more than one term, like he did when he snuck, if we go back up here, where was it? He snuck right angle into definition 10, where he said it was going to be a definition of a perpendicular, and then it turned out to be a perpendicular and a right angle. He does the same thing, but even more so with some of these definitions coming up. So we're slowing down a little bit in terms of the official definition numbers, but only because we're going to be packing lots of new terms in, and I want to go slow enough to make this work. Okay. So, just again, as quick review, so far we have said that a point is that which has no part. That is to say, a point is location without length or depth or width. A line is length without width or depth, obviously. So if you take a point and then you give it length, you have a line. The extremities of the line, though, are still points. And a straight line is a line that lies evenly with all the points on itself. Then a surface is what happens when you take a line and you give it width. So you take a point, give it length, and it becomes a line. Give a line and you give it width, and it becomes a surface. We said that both of these are surfaces. It doesn't need to be regular or pretty or anything. You can have a Waukesha ugly surface. The extremities of surfaces are lines. So in the same way that the extremities of a line are points, the extremities of a surface are lines. A plane surface is a surface which lies evenly with all the straight lines on itself. So hopefully that you remember that. And then a plane angle. We introduced angles in definition 8. A plane angle is the inclination to one another of two lines in a plane which meet one another and do not lie in a straight line, because that just makes a straight line. And it doesn't, it sort of overlaps, but they don't take up any space. A rectilineal, then, is what you get when you have angles made between straight lines. Pretty straightforward there. An obtuse angle, a perpendicular is what happens when you set up one straight line on top of another straight line in such a way that the angles between them are equal on both sides. And when the angles between them are equal on both sides, we call those right angles. An obtuse angle is an angle that is bigger than a right angle, and an acute angle is an angle that is smaller than a right angle. A boundary is that which is the extremity of anything, so the edge of anything is called a boundary. And a figure is anything that is contained by boundaries. One boundary in the case of a circle, or more boundaries in the case of a triangle or squares or anything else. We're going to actually later on, not today but tomorrow, we're going to see lots of new that will get special names for different figures. A circle then is a plane figure contained by one line, such that all the straight lines lying upon that one line from one point among those lying within the figure are equal to one another. And we spent a lot of time trying to define that and unpack that last class, and I hope it was pretty clear. I didn't get any questions on it, so I'm assuming you felt good about it. And then we said that point that all of them go through, that is the center of the circle. All right, so with all of that in place, let's go on to definition 17. In definition 17, Euclid decides he's going to define a diameter. All right, so here's how that reads for Euclid. A diameter, let's see where of the circle is any straight line drawn through the center and terminated. I will terminate you. No, and terminated in both directions by the circumference by the circumference of the circle, comma, and, by the way, he says, and such a straight line also, special term, bisects the circle. All right. Let's, first off, since we added a term here, we're going to go ahead and add it up here. So diameter and bisect. Okay. So for this, since we're dealing with circles, we're just going to grab all of this, boom, and pop it in here. And notice that we're going to have to move some things around to make all this work. Just move up diameter and bisect here a little bit. That way, that works. That all works nicely. Okay. So we've got our circle on a plane. I'm going to go ahead and get rid of my center dot here. And we already know this is a circle, so let's get rid of that as well. And let's see what we've got now. Okay, so diameter of the circle is any straight line. We've got a whole bunch of them here. Straight line drawn through the center. All of these, remember, are drawn through the center and terminated in both directions by the circumference of the circle. So what that means is the end of the line is also the circumference of the circle. And we said that we did, and indeed, we did do that. So fix some of these here, but we did do that. So the ends of each of these lines ends at the circumference of the circle, and such a straight line also bisects the circle. Okay, I'm going to come to that bit in a second, but first let's just really quickly. So we only need one line to be the diameter, so let's go ahead and get rid of some of these lines. All right. Oh, there we go. So we know that this one does go through the center of the circle. I demonstrated that too already. So a diameter of the circle, any straight line check, drawn through the center, check, and terminated in both directions by the circumference of the circle. So it ends on the circumference of the circle, check, therefore it is a, there we go. Therefore this is a straight line. Okay, that sounds nice and makes us all happy. I can play around with this just a second. All right, yeah, that's okay. Okay. So far so good and not too hard. A diameter is any line, straight line drawn through the center of a circle that ends on the boundary of the circle. Okay, but Euclid also wants us to know that such a straight line bisects the circle. Bi means two, sect, think section. So two sections. It cuts the circle into two equal sections. And that's going to be really important for us in just a second. Sort of, he's lining up the next definition for us. Really, is what he's setting up. So notice that in this case we have one circle bisected by a line, and we're going to call that line, instead of giving it a fun name, which I know it's been fun and I like calling them Bob and Wanda and Humphrey and so forth, but we can't do that anymore. We're going to have to get all mathematically careful, and we're going to call this line DH, because it connects the points D and point H. It's traditional in geometry speak to name a line based on the points at its ends. So point D and point H are the 2 points at the ends of this line. They are the boundaries of the line, to use proper terminology. So line DH, we know, bisects the circle. Ta-da! All right, that was exciting. Let's go ahead and move on to definition 18 now. Definition 18 is the definition of a semicircle. A semicircle. All right, so you ready for this? Here we go. According to Euclid, a semicircle, if I can spell it, a semicircle is the, I think I have one too many spaces there. I can fix that. Is the figure contained by the diameter and the circumference cut off by it. And Euclid wants us to know the center of the semicircle, this will take you a moment to get your head around, by the way, is the same as that of the circle. All right, this is going to be really This might blow your mind for just a few seconds. We'll see if we can get it. Or it might just frustrate you. And by the way, I want to take a moment here for a second and just let you know that it is completely okay to be frustrated by Euclid sometimes. There are great mathematicians out there who have been frustrated by Euclid. Being frustrated by Euclid is an honest pastime for geometricians. So if he says something and you're just thinking that does not make sense and I don't like it at all, that's okay. You're allowed to think that. But it is still important to try to understand what exactly it is that he's doing. Okay, I'm going to go ahead and get rid of that for right now. We might bring it back later. All right, so what is a semicircle? According to Euclid, do I even have a semicircle I can use? I don't think semicircle is a shape they give me. This one might be. Yeah, well, they give me a partial circle. I bet I can do this. That's not going to work. Well, I bet it will actually. I bet they let you do that. They do. All right. Okay, we're gonna do this, guys. We're gonna do this fun. All right. So here we go. Let's get rid of lines B, F, A, E, and C, G. We'll get rid of the letters for them too. I guess I should probably really I just should have copied. I copied the wrong illustration here, didn't I? Okay. So we're back to where we were with line DH bisecting the circle. The circle. Okay. But what do we need to know? We actually need a semicircle. So, according to Euclid, the semicircle is the figure contained by the diameter, that's DH, remember DH is the diameter, and the circumference cut off by it. So, this part is cut off by it. So, you actually have two semicircles here. You have semicircle, well, you have two semicircles, and both of them are DH. DH, and I guess you call the one HD if you wanted to. So, let's go ahead and let's go ahead and insert one of those partial circles here. Don't need a chord. Chords are fun. We'll do one later. Okay. So for this, we need a semicircle. It's going to be... Oh, I see what they're doing to me here. In fact, what we're going to do here is we're going to make this circle exactly fit onto circle DH. Oh, no, that's not what I wanted to do. Don't do that. Come here, semicircle. Playing around with this thing a little bit here. And there we go. Okay. Now, I'm going to do that. And what I want to do now is rotate this sucker. Oh, you know what? It's telling me that I didn't actually do a circle properly. It's very angry at me about it, too. It doesn't think I drew a circle. Now it thinks I drew a circle. Alright, it thinks that's a circle, and it's probably right. Okay, so here's my semicircle. Fits neat. Oh, not quite. There we go. There we go. Alright, so there's my semicircle fitting almost perfectly onto my... Why won't you fit perfectly? Come on, fit perfectly for me next time. I want you to fit perfectly. You know what you're doing. Fit perfectly for me. Here we go. There we go. It's still not... Well, we'll call that good. Alright, and there's my semicircle. So now we have line DH, which is separating, and in fact what's interesting is we can actually take off the line part of it. Boom. And watch that. Watch this. Here we go. So now you have a proper line. It has no width again now, like a proper line shouldn't. Just stop futzing with this. Come on, Bill, stop futzing. Okay, this is good. This PowerPoint's going to let me do it. But I have a line DH, and it's bisecting the circle. And you can see that we have a semicircle. Now, here's the part that I said was going to kind of blow your mind a little bit and might make you angry with Euclid. He says the center of the semicircle is the same as that of the circle. What he means is that that same point that was the center of the circle is also the center of the semicircle. That is to say that the semicircle's center is right there, and I'm going to change its color to make this. I know it looks just like a Pokeball now. You'll be okay. There we go. So there we go. That's the center of the semicircle. Even though I know you want to put the center up here or something, but when you think about it, there's no point in the semicircle that is equidistant from all the edges of the circle except this point is equal from all of the edges of the circumference of the circle part of the semicircle. It's not equal distance from all the points on the straight line, but it is equal distance from all the points on the boundary of the circle part of the semicircle. And that's as close as we can get to something that feels like a center. So even though it isn't really in like what might feel like the middle, it's still considered the center of the semicircle. And it's still going to be considered the center of the semicircle, even if I get rid of the circle altogether. This is still the center of the semicircle, as frustrating as that might be. I'm going to bring it back there, and so there you go. So that is the center of the semicircle, and you do need to know what the center of a semicircle is. Okay, frustrating or not, we got to move on. Let's go on to definition 19. And definition 19 is a little bit more complicated because we're going to define a lot of terms here. In definition 19, we want to define a rectilinear figure, rectilinear, trilinear. I know it says I spelled that wrong, but I didn't. I thought it's not like I'm sorry. We want rectilineal. Rectilineal. There we go, and it's fine with that. Trilineal, rectilineal, trilineal, quadrilateral, and multilateral figures. All right, I think I spelled trilineal right, but I'm wrong. It's not lineal, it's trilateral. See, this is why it's good to go back and check yourself. Trilateral, rectilineal, trilateral, quadrilateral, and multilateral figures are all going to be defined here. So we've got a heck of a definition coming. Just get ready for it. In fact, let's just, in preparation for it, we're going to move this up a little bit higher, just because we know we're going to need the extra space. Okay, so here we go. According to Euclid, rectilineal figures are those which are contained by straight lines. Yay! Comma. Trilateral figure. Ooh, I need that to be in italics. Oh, that was not the thing I wanted to do. Trilateral figures being those contained by 3 quadrilateral, those contained by 4, and multilateral, lost my place, those contained by more than 4 straight lines. Okay, so let's go ahead and make some figures, because these are easy figures to make. Okay, so any figure which is contained by straight lines is a rectilineal figure. So what we're going to do is pull this one up here. Let's get a non-rectilineal figure, our Waukesha wrench thing. All right, Waukesha wrench thing is totally a figure. Here it is. Look at that. There's Waukesha wrench thing. I'm shrinking them down, but Waukesha wrench thing is 100% a figure. Right, so let's go ahead and say figure. Right, it is. In fact, he's a plane figure. Right, but he is not rectilineal. Okay, so let's go ahead and just to make this clear, right? So I think I got a check mark somewhere around in here. Give me my check mark. Check mark. Check mark. Check mark. Check mark. Check mark. Oh, come on. I wanted a check mark. They didn't give me a check mark. That's not nice. All right, then. So we're going to say that it is a plane figure. Yes. Let's have to do it this way. Plane figure? Yes. Rectilineal? No. And it's not a rectilineal figure because it is not, there's curved lines, right? And they would all need to be straight lines. So rectilineals are those which are contained by straight lines. The boundaries have to be straight lines in order for it to be a rectilineal figure. However, right, but it is a plane figure. That just means it's a figure on a plane. Okay. So let's go back then, and let's say that Let's make a new figure though. Trilateral figure. By the way, there's no such thing as a bilateral figure because that you can't have just two sides. Weirdly, you can have one side. I guess you could. In fact, a bilateral figure. What am I saying? Would be a semicircle. But we're not worrying about them. Trilateral figures are those which those contained by three sides. So let's go ahead and make one of those. We know what they look like. They look like this, right? And we don't want them all to be the same. Let's make this one green. Right? Oh, and no outline. We don't do outlines here. No outline. Okay, so here we go. Here's a trilateral figure. I'm just going to do the copy and paste this box. All right, so here we go. This is a plane figure. Yes, it is also rectilineal because those lines are straight, and it is trilateral. Yes, it is because it has three sides. Straightforward. It's contained by three sides. Okay. A quadrilateral are figures contained by four. So let's go ahead and get ourselves a quadrilateral figure. Here is a quadrilateral figure. Right? Straightforward. Pull this one up here. Is it a plane figure? Of course it is. Is it rectilineal? Yes, it is. Is it trilateral? It is not. Because it's not contained by three sides. It is, however, a quadrilateral. Because it's contained by four sides. All right, so there we go. It's a plane figure, it's rectilineal, and it's quadrilateral. Okay. Let's see here. Okay, so that's exciting, and I'm sure we're all very, very thrilled. But we still have to do a multilateral. So let's put in a multilateral figure. I think we have some pre-made ones I get to play with if I want to. We do. Here's a nice one. There we go. And this has more than four sides. In fact, it has 1, 2, 3, 4, 5, 6 sides. This is a hexagon. 1, 2, 3, 4. No, it's got 5. I was right. Okay, 5 sides. 5 sides. So is it a plane figure? It is. Is it rectilineal? It is. Is it trilateral? No, it's not. Is it quadrilateral? It is not quadrilateral either. And also, we need new colors for these. What am I thinking? I forgot to fill this one with. Let's make this one red. And again, we don't believe in outlines here in geometry. And let's make this one. Do I have a pink? I want pink. In a while. Let's get some more colors. Pink. There we go. That is a really pink. And we don't believe in outlines. No outlines. Okay. So it's a plane figure. It is rectilineal. It is not a trilateral. It is not a quadrilateral. It is instead multilateral. Yes, it is. Okay, so plane figure, yes. Rectilineal, yes. Trilateral, no. Quadrilateral, no. Multilateral, yes. So those are 4 kinds of figures. Now I want to do some things really quickly. I think that's actually about all I wanted. There are differently sized, and you can really play around with this a lot if you wanted to. So if we were to, for instance, let's in fact, what we're going to do here is I'm going to shrink all of these down. I'm just going to there we go. All right, watch this. So now I've got. Let's play around a little bit more because I want you to see some of the variety here. Okay, see how that works. All right. Actually, it's this one. We can just make this one bigger again. That's fine. We're not going to play around with the plane figures. But let's look at trilaterals. Remember that to be a trilateral, it just needs to be a rectilineal figure with 3 sides. So that's a trilateral, yes. But also, what happens if I make it just taller and skinnier? And the sides aren't equal anymore. Is it still trilateral? Yes, it is. Okay, so just so you know, both of these are still trilateral figures. It doesn't need to be what we're later going to call an equilateral triangle. That'll happen eventually, by the way. What about this one? That's a terrific trilateral, or quadrilateral figure. I can't speak anymore. But so is this. No, this is a nope. This is going to go over here. We're going to play this one here. This is not a terrific trilateral figure. It's a different thing. We'll come back to it in a second, though. Let's leave it. We won't need to delete it. And let's get ourselves a more interesting. Where's the one I'm looking for? If I'm allowed to do the one I'm looking for, here's the one I'm looking for. There we go. Here is a nice quadrilateral as well, right? So this is a quadrilateral. Go back to our red. Right? No outlines. We do not believe in outlines. Okay, so here we go. Here's a red. It's quadrilateral. It's got 4 straight lines. And so it's quadrilateral. It's four straight lines, and that's all really neat. Then we have a 1, 2, 3, 4, 5, 6 straight lines here. Let's go ahead and go. Fine, we don't believe in outlines, but let's go ahead and make this the same color. Okay, so we've got 1, 2, 3, 4, 5, 6 straight sides. So it's multilateral and it's rectilineal, even though they are not regular. Those sides are not what we call regular. The sides aren't all the same length as each other. They're all sort of different, and some of them are at angles, but they're all straight lines. So this is still a multilateral figure. Okay. See what I mean about we needed to slow down here a little bit because there are going to be so many definitions. All right, we're going to do one more set of definitions, and then we're done for today. But definition number 20. Here we go. Here we come. We can. I think you can handle this. We got definition 20 coming right up. Definition 20 is going to define equilateral. I told you it was coming. Isosceles, and scalene triangles. And let's just shrink all of that just a tiny bit so that it fits. And then we're going to go like that. All right, so we're going to define equilateral, isosceles, and scalene triangles. Hopefully, you're kind of used to some of these definitions, but I want to point out ways that Euclid uses them in special ways. So, Euclid. By the way, Euclid, I think I may have mentioned this before, but he is an ancient Greek geometrician. All right, the father of geometry, they call him. Okay, so we're defining equilateral triangles, and this is definition 20. So of, what he says, what Euclid says is, of trilateral figures, so this is only relating to trilateral figures from the one above, of trilateral figures, and I realized those should have been in italics, and I just spelled figures wrong too. I can fix all my mistakes, people, I promise. Of trilateral, I was just deleted, it was repeated. Okay, of trilateral figures, and equilateral, oh, I see what I did wrong. Let's just equilateral triangle. It's been a rough day, folks. Okay, actually these aren't being defined here, so we're going to just leave that there. An equilateral triangle is that which has its three sides equal. There's equal. It's that which has its three sides equal, comma, and that is a terrible word to spell. Isosceles. The C is silent because it makes the S sound, so it's not isosceles, it's isosceles. Triangle. That which has two of its sides alone equal. You know what a scalene is going to be then? And a wrong button. Scalene triangle. A scalene triangle, that which has its three sides unequal. Sorry, I had to pause there because we had an interruption, but it's okay. Everything's back on track. Okay, so let's go ahead and make some triangles. An equilateral triangle, according to Euclid, is that which has its three sides equal. So let's go ahead and drop an equilateral triangle in the mix here. Here, I think, is probably an equilateral triangle. Let's just say, let's call these lines, well, let's give our lines some, I like to keep my triangles green, and we don't believe in outlines here. All right, so we have three lines here, right? Let's go ahead and label them. So we're going to go ahead and do this. To make this work, we're going to need some letters. All right, but this D, nobody starts with D. Let's start with A. All right, we'll say that's point A is the tip of the triangle there. There we go. And let's get some point B. All right. And let's grab point C. All right. Okay. So we need an if-then. We need some if-then statement H going here. All right, so ready? If, let's say, let's call it A, line AB equals line BC, and also, which also equals line CA. If that's true, then triangle, I don't think I can make then. I'll just say it is, then we'll call it ABC is an is equilateral. Right? Let's send those. And this one. There we go. Okay, so if line AB equals line BC, which equals line CA, AB equals BC equals CA, then ABC, triangle, is equilateral. Make sense, everybody? I hope so. Let's move on. But remember that if any of this doesn't make sense, ask me a question about it in comments, and I'll go back over it the next time I get a chance. Okay. Next, after that, let's put another triangle on the board here. How it just kind of looks. I haven't checked it, by the way. There is a way to check it. We just haven't learned that way yet. All right. So here we go. This, we are told, is an isosceles triangle. Now we can be pretty sure this is an isosceles triangle because, in fact, we'll still do it that way. I mean, we can still do it. Remember, we like our triangles green here, but this is a darker green, and we don't believe in outlines. Okay. So let's go ahead and copy this. This is not quite right, though, because we don't want an equilateral triangle. We want an isosceles. So we need here is... that was the wrong thing. Still got to label our points. We can still call them A, B, and C, though. All right, so here's A, B, and C. All right, if line AB equals line CA, right? Isosceles is that which two of its sides alone are equal. So we have to do an and. And line CB is not equal to AB or CA. There we go. Then it is isosceles. We got to change collateral to isosceles. Then it is isosceles. There we go. Then triangle ABC is isosceles. All right. So if line AB is equal to line CA and CB is not equal to AB or CA, then ABC is isosceles. So you need two lines that are equal to each other and one line that is not equal to the other two to have an isosceles triangle. Finally, we want a scalene triangle. Let me see if we can insert a scalene triangle automatically that we know will be scalene. Isosceles triangles, right triangles. I think we have to make ourselves. We might have to make. Let's see. No, tough to say. We might have to make a scalene triangle. Scalene triangles, they don't like giving us here. Let's see. It's going to be an isosceles. All right. Let me see if I can find myself. How are we going to do this? We're going to have to make it. We can do that, though. Making isosceles triangles is fairly easy. We just need our sort of draw-y tool. And let's make a triangle. All right, so we're going to make an isosceles triangle. There we go. There is our isosceles triangle. We need to fill this one with, let's go to the super... where's my greens? I am colorblind, and green is not a great color for me to be trying to do. There we go. That's a nicely sort of bluish green. We'll use that one. And we do not believe in outlines. Okay. So, let's do this. Define this one again. And again, we're going to need these letters. Here's point A. Here's point B. And here's point C. Okay, so now if AB is not equal to CA and say or CB, and CB is not equal, oops, sorry, it is here, let's fix up this notation here, is not, and CB is not equal to CA, that's all we need to say now, and CB is not equal to CA, then ABC is scalene. That is a really complex way of saying if none of these are equal, then it's scalene. You know what? This it's almost, anyway, there. Now it's, there we go. Now it's definitely scaling. I don't know how I flipped that upside down. I just wanted to move it. There we go. Okay. So now it's definitely scaling. All right, so if AB is not equal to CA or CB, AB is not equal to CA or CB, and CB is not equal to CA, then ABC is scaling. And in this case, ABC is scaling. All right, so we got 3 triangles today. We defined multilateral, quadrilateral, and trilateral, and rectilineal figures today. We defined a semicircle today. We dealt with the frustrating fact that the center of a semicircle is not in the middle of the semicircle because there is no middle to a semicircle. And we defined diameter and bisecting a circle today. So we got a lot of work done. We got a lot under our belts, and that is going to do it for today's class. Tomorrow, we actually will finish the definitions and move on to the postulates the day after that. So very exciting, and I hope you're still enjoying it.